Ti plus 1 TL. And this is identity, as I call it, the identity of Sn. Right? And so these moves actually keep the product invariant. Moreover, it turns out that they also keep their transitivity invariant as well. In other words, these transpositions also generate the entire group Sn. So everything is sort of preserved. And we say that two factorizations of identity are Hurwitz equivalent if there exists a finite sequence of Hurwitz moves defined like this, such that one can be transformed into another. And then we also define the inverse Hurwitz move in the obvious way. You move it backwards, and instead of conjugating it by Ti, you conjugate it by the inverse of Ti. It's standard. It's kind of like going backwards. So these are the fundamentals of everything that I was dealing with for the entire summer. This very sort of abstract thing. And these correspond actually to the points on the sphere where you have these quote-unquote discontinuities, these branch points. And the transposition actually have something to do with certain, if you have a base point and you take certain loops around them, right? And under certain transformation, this forms a group. And this is where these come from. But again, that's the geometry. I didn't really get into it.
If there is time, I'll explain this.
Yes. Which is very interesting and very nice.
Very nice topology. What he does here, he translates in algebraic terms something that we see topologically with covers of Riemann surfaces.
So let's see what's next. Okay, so what he gave me, well, we have this sort of idea of Hurwitz equivalence. Several papers have been written on it, so if you Google it, look it up on any sort of archive, you'll find that there are some papers written on it. But not many of them refer to the symmetric group. Some of them have to do with the dihedral group, the rotations of a regular polygon in the plane. And some of them have to do with free groups, and so on and so forth. So there's actually very few papers having to do with the symmetric group. And there was one that I used a lot by Benitzak and Teicher that was very useful. I'll mention it again because they have some very nice results that I end up using. But in order to facilitate my study of Hurwitz equivalence on the sphere, or in the symmetric group, I'm sorry, what Dr. Seidel did was sort of encode all this information onto a graph. And so at this point, I'll define the graph. The graph itself is it's written up there. So you have the vertex set of the graph. So I'll denote that VG is actually the set of all these tuples, however you might pronounce it, such that all of the characteristics that I mentioned in the first slide are satisfied. They have to be transitive, they have to multiply out to identity, and they have to be transpositions. Okay? Now the edge set is also defined in a pretty standard way. So let's say we have two of these tuples. So we have Ti to TL, comma, S1, SL. This is an edge if there exists a Hurwitz move that transforms one of them into the other. A single Hurwitz move. Just doing this sort of like transposition and conjugation. If there exists a single one, you define an edge. If they're Hurwitz equivalent, there's a path. Right? And so such that it's sigma I T 1 plus or minus 1. Could be inverse. TL equals S1. S. Okay. So far, so good. now we have a nice little object, a nice language to talk about everything we want, right? So we care about things sort of like the order. We care about the diameter. We care about paths. We care about everything about this graph. And in math in general, you define an object, you want to know everything about it, right? That's what we do. So, indeed, that's what they set me out to do. They put me in a room, they said, go, let's figure everything out. And the first thing they asked me for was the order of this thing. The order of this thing is, in other words, the number of these tuples that exist on the graph, all right? Which is not a very simple problem to begin with. It's sort of like an algebraic, it's a combinatorial problem. You have to figure out how many factorizations of identity there exist, right? You also have to figure out how many of them are transitive, and so on. These aren't immediately known questions. At least we didn't know, and we couldn't find it. So I had to figure it out. So the natural question to consider, like I said, was the order of the vertex set. How many of these exist? Because if we know how many of these exist, then maybe we have some information about how far away any two different factorizations can be. You see? And the ultimate question is to determine that, how far away they are. How to transform any factorization into a Hurwitz equivalent. And if this is actually a very difficult thing to do, or if in fact it's straightforward. So here we go. So I started to attack this problem by determining the total factorizations of identity. Right? And this is, I was able to find some information on this for small n. Right? So if you have a symmetric group of n letters, on n letters, for 3, 4, or 5, there exist these sort of closed forms. I was able to find them. But other than that, I wasn't able to find too much information on it for anything higher than 5, let's say, right? And so I spent some time working on this problem. And I'll spare some of the details and move on to the actual computation, because there's a lesson to be learned here. So I don't know what to erase it. So what ends up happening is that I define this notation. That's, it's up there. And I care about determining the number of factorizations of any even permutation. Even permutation is a permutation that can be written as a product of an even number of transpositions. Guys like this, right? And a sort of immediate consequence of the fact that this multiplies out to identity is the fact that the length of these tuples it's even. Right? It has to be even because the identity element can be written as the product of two transpositions, which is even. See? So clearly this is an even number. So what ends up happening is that tinkering, and trying to figure out a combinatorial way to get a solution, I get this sort of recursive relationship between the number of factorizations of small values and any value. So it turns out that there's an m. There's a sort of minimal natural number so that every even permutation can be expressed as a product of m many transpositions. And this is the case because of the fact that we have a finite number of elements in the symmetric group, and because of the fact that I find the maximal one, so I'll write it down. So let's say alpha 1, alpha 2, and so on, alpha n factorial over 2 are all the elements of the symmetric group that are even. There's half of them are even, right? Some of them I can express maybe as T1 1 times T2, let's say. Some of them I can express as T1 2, T2 2, all the way to some other number, right? Let's call it M1 or M2 in this case. Let's call this M1 and so on. and I list them all, right? So I list them all. So what is this? In factorial over 2. Tm n factorial over 2. And I find the longest, right? They're even. So what I do is, to the ones that aren't that long, I just multiply them all by the transpositions 1, 2, 1, 2 repeated until I get to that length. Make sense? So that way, there is a minimal m so that all the even permutations, they're also called members of the alternating group, can be represented or can be factored into transpositions. And this is this special m that you see listed everywhere. So what ends up happening is, seeing this recursive relation, it turns out that it only depends, the number of factorizations of even permutation only depends on this m. So if we calculate this m for each element of the alternating group, we actually can encode this into a matrix and sort of take powers of the matrix times some initial vector r. And this actually gives us the number of factorizations of any even permutation here of length L, where we only have to compute this very relatively small m, which is around the size of n itself, actually, which is another proof. Which is kind of nice, that we were able to reduce something that was combinatorial, something that was actually an algebraic problem to begin with, into a linear algebra problem, right? And we can have an explicit closed form for all of them if we determine the eigenvectors of this matrix, which is kind of nice. Moreover, this is a symmetric matrix if you look closely. Since it's symmetric and all the entries are positive, there's this nice theorem by Perron-Frobenius that says that there is an eigenvector always that has only positive entries. And this is the eigenvector with the largest eigenvalue. And this is actually very important because my project actually cared more about large N and large L, particularly large L. So we care about the asymptotic behavior of these graphs. How big are these paths when everything is large, when N is large, L is large, particularly L large. And so, knowing this, we know the asymptotic behavior, because if the biggest eigenvector of this matrix is of a certain type, then we know how each different factorization of the even permutations is going to act asymptotically. And it turns out that the eigenvector here is 1, 1, 1, 1, 1, 1, 1. So what does that mean? It means that at infinity, it evens out. They're all roughly equal as you take a limit. And in fact, I think that's the next lemma. Yes. So I proved this. So what do I learn from this, other than this all this technical stuff? What I learned was the fact that I was looking in one place for a solution. All of a sudden, boom, different place, matrix, eigenvalues. Look at the relationships between the coordinates of the eigenvectors and so on. And all of a sudden, something completely unexpected. I was just looking for a combinatorial proof. I find this sort of thing. So the lesson is, keep your mind open to analysis. If you're doing algebra, think of analysis. Think of geometry. Think of everything. Everything is a tool, right? And since there's a lot of new faces, yes, then it's something to keep in mind. A lot of times we only want to focus on one thing. We only want to focus on analytic number theory. We only want to focus on geometry, right? Anyhow, so we proved this lemma. And we know more or less, asymptotically at least, the order of the Hurwitz graph.
Okay, just a second.
Yes.
We means you.
We is me.
Yes.
Yes.
The kings usually
Yes, this is a royal we.
speak of themselves.
Okay. And so the next thing I showed, and I showed it actually via probabilistic